This is the brief on using the Dirac delta function to describe localized charge. The Dirac delta function is this incredibly useful tool in physics. Think of it like a pin on a map. It helps us describe a charge that's packed into a single point, or maybe along a line, or on a surface. The tricky part, though, is making sure it works correctly when we're not using a simple grid, but instead, say, spherical coordinates. That's where you've got to be careful. First up, there's dimensional invariance. All this really means is that your units have to make sense no matter what coordinate system you're in. Your charge density has to always come out as charge per volume. It's a simple but absolutely crucial reality check to make sure your math isn't giving you nonsense. Second, let's talk about geometric localization. This is pretty much the main job of the delta function. It pinpoints exactly where the charge is. So if you've got charge on the surface of a sphere, you can use the delta function to basically tell your equations, hey, forget everything else, just focus right here on this surface. It turns a messy volume problem into a much cleaner one. And finally, we have the role of normalization factors. Now, when you're in those curvy, non-Cartesian systems and you split up the 3D delta function, you have to toss in a special correction factor. It's all about making sure that when you add everything back up, your total charge is correct. Without it, the weird geometry of the coordinate system will throw your whole answer off. So keeping your units consistent, using the function to pinpoint the geometry, and adding the right correction factors, that's the key to modeling charge distributions correctly in any coordinate system.